So this presentation is about third-party security patches and the hot patching techniques used to implement them. In the next hour, we'll talk about three specific areas. First, we'll do an overview of the recent developments in the third-party patches starting from December 2005. Then we'll talk about the implementation techniques. We'll briefly cover the Microsoft hot patching implementation. And finally, I'll talk about the vulnerability analysis techniques that I used to develop these hot patches. At the end of the presentation, there will be a demo where I will analyze a security vulnerability from scratch, and I will build a hot patch for it in about 15 minutes. So in this talk, when I say hot patching, I'm referring to a specific method for modifying the behavior of a program by modifying its binary code at runtime. That's not a new thing. It's been used for many years. Most debuggers use a hot patching technique to implement software breakpoints. It's also used for instrumentation, hooking API functions, cracking software, cheating at World of Warcraft, and most recently, deploying software updates, including fixes for security vulnerabilities. And this has been done by both vendors and by third parties. And this is what we're going to talk about today. In the last 8 months, I guess, we've seen three third-party security patches. The first one was the WMF patch written by Ilfak Gulfanov. Most of you probably know, but Ilfak is the author of IDA Pro, which is a widely used disassembler, fairly popular in the security community. This was the first patch that got a very wide deployment and generated a lot of buzz. So 3 months later, it was followed by two more developed independently by EI and Determina. This time they were for the Internet Explorer create text range vulnerability. So let's look at the vulnerabilities that these third-party patches fixed. The WMF vulnerability was interesting because it was found in the wild, and when it was first reported on the public security mailing lists, it was already being actively exploited and used for malware distribution. So it was fairly critical. Another thing that made it worse is the fact that the vulnerability was not a result of memory corruption like most buffer overflows are, but instead it was a feature of the WMF file format. This feature allowed the attacker to put arbitrary code in the file that would get executed whenever the file was being displayed. And Internet Explorer could be used to display these files if they were hosted on a web page. So it took Microsoft 10 days to release a patch after the initial reports of the vulnerability. Ilfak Gulfanov released his on December 31st, beating Microsoft by about a week. His patch consisted of a small DLL that was loaded into all processes using the AppInit DLL's registry key. This little piece of code loaded GDI32, patched an exported function in it, and this function, the exported function that he patched, was responsible for handling the WMF records that contained the arbitrary code. So Ilfak's patch added an additional check that looked for that executable code and aborted the processing of the file if it was found. It's also interesting that when Microsoft released their patch, it was not exactly the same, but fairly close to Ilfak's. So this incident showed that it is indeed possible for a third party to patch a security vulnerability and get it mostly right. So 3 months later, we saw another security vulnerability affecting Internet Explorer, and that seemed suitable for hot patching. This time there were two security companies who decided to develop these patches. The vulnerability had been disclosed to Microsoft. It had been reported privately about 2 months before the patch came out, but about a month later it was disclosed publicly, and then we started seeing exploits for it. It turned out that the vulnerability is fairly easy to exploit, and the Metasploit project had a working exploit code for it a few days after the vulnerability disclosure. So again, we saw the two third-party patches being released about, I guess, 2 weeks before the Microsoft patch. The two patches were by EI and Determina. So let's take a look at what they did. The EI patch was slightly different than the ILFAC patch in its approach, because instead of modifying the application in memory, it created a copy of JScript DLL, and it patched it on disk. It used a pattern matching technique to find the instructions in the file that needed to be patched, and then appended a little bit of code to initialize an uninitialized variable, which was the cause of the vulnerability. It also modified the registry to force Internet Explorer to use the patched version of the file instead of the real one. The Determina patch, which I wrote, was closer to the ILFAX patch in its mode of operation. Again, it was a little DLL that was loaded into all running processes. It intercepted the loading of MS-HTML DLL where the vulnerability was, and patched a function in that file. Instead of using an exported function or pattern matching, I had a list of hard-coded patch points for about 98 different versions of MS-HTML, and these patch point locations were determined using an in-house tool we have and a big database of all Microsoft DLLs. On most versions of MS-HTML, it was sufficient to modify a single byte in the vulnerable function to fix the vulnerability. Instead of adding additional code to add a new check, I just redirected a conditional jump to go to a different place where the code already existed to fix the vulnerability. So, having looked at these third-party patches, the question arises of why should you use them? What are their advantages and disadvantages? Obviously, if the vendor patch is not available, then a third-party patch is a good alternative to protect yourself. In this, third-party patches are competing with other security systems, such as network-based intrusion protection systems and others. One advantage that the patches have is that they fix the vulnerability on a very low level, modifying the code exactly where the vulnerability happens. This makes them exploit independent, because unlike a lot of signature-based systems which rely on standard shellcode patterns or something like that, the third-party patches fix the actual vulnerability, so they don't really care about what kind of exploit is being used as long as it exploits that hole. This also makes them not vulnerable to evasion, which is fairly successful against network-based IPS systems, and I think HD had a talk about that at this conference. The disadvantage of the third-party patches is mostly related, the disadvantages are mostly related to the insufficient resources that the people producing them have. Obviously, a fairly small company like ours does not have the resources of Microsoft to do QA testing on the patches. Also, support for multiple OS versions and languages, different language packs, is also limited, again, because of limited resources. Another problem is that some of the vulnerabilities require very extensive changes to the application, including, like we've seen Microsoft patches where they completely redesigned a subsystem of the application to fix some sort of design vulnerability. So obviously, things like this will be very, very hard to hot patch, most likely impossible. So we're not going to see hot patches for every single vulnerability, just the ones that are more well-suited to that technique. However, even given these limitations, I believe that third-party patches are a good option, especially for the cases where the risk of system compromise is great, but the risk of interoperability problems or the impact of interoperability problems is not that big. I believe that most enterprises already do have a QA cycle for the official patches, so maybe a similar QA cycle can be used for the third-party patches as well, remediating some of the QA problems. Another question that often comes up is about the issue of trust. I get this especially from the press. They ask, why should we trust this company with patching our system? Well, you have to realize that most commercial software which you run on your system is, especially security software, is pretty intrusive and might do things that are even more dangerous than the third-party patches. In fact, all three of the patches that I talked about were very, very small, very self-contained, and they also included source code which could be reviewed to make sure that the patch really does what it intends to. I think the small size combined with the availability of the source code makes it much easier to verify that the patches are actually good and trustworthy as compared, for example, to a large closed source application. So now we're going to move on to how to implement these hot patching systems. The simplest form of hot patching is to just modify the code in place. You can use this to remove code from the application by overriding its instructions with knob instructions. You can also use it to replace some instructions with others. One limitation here is that the instructions have to be, you're limited in size. The instructions have to be of the same size or possibly smaller. You cannot add new code to the application. And the classic example for changing an instruction is if you have a program with a license check, and after the call to the function that checks the license, you have a conditional jump that lets the program continue, or it aborts it. If you replace that with its opposite conditional jump, then the program will work when the license is invalid instead of the other way around as it was designed. If we want to add code to an application, we need to use a different technique, and the one most often used is the 5-byte jump override. This is very common for hooking API functions. In this case, in this example, we have a function, and we see the standard function prolog in the beginning, and then we override the first 5 bytes of the function prolog with a jump instruction that goes to our hook. This means that whenever somebody calls the function, our hook routine will be executed, and we get to do whatever we want it to. Most often, after we execute our hook routine, we want to return back to the original function and continue its execution. Maybe we've done some logging, maybe we've modified some of the parameters, but we still want to go back to the original function. To do this, we need to save the instructions in the first 5 bytes, the instructions that we overrode. So we make a temporary copy of those instructions, and after the hook routine does its task, we need to execute the saved instructions and then jump back to the remainder of the patched function. And this will make sure that the stack frame of the patched function is established correctly, and it should work as if nothing had happened. There's some limitations when you do a 5-byte jump override. There are some limitations to the patch, to the locations that you are allowed to patch. The obvious limitation is that if you patch some data in the program, then the program might try to read it or write it, and it might override your jump instruction, thus rendering it invalid. This doesn't happen very often in compiled code because the compiler doesn't really use the same bytes as code and data, but if you have a packed or somehow protected application, you might get into this case. The other limitation is that the 5 bytes that you override cannot cross a basic block boundary. This means that nobody else in the program should jump into the middle of these 5 bytes, because if they do, they will jump into the middle of your jump instruction, and most likely the program will crash. Another limitation, if you're doing the patching while the program is running, that's not a problem if you're patching it before the program starts. But if you do it after the program is running and you have a call instruction and you override the call instruction and the bytes following it, your jump instruction might coincide with a return address that's saved on the stack. Because if that call instruction was executed previously, the program might be somewhere in the callee, and on the stack it'll have the address after the call instruction. So if you do the patch now and then the program returns back to that address, it will return into the middle of your jump instruction, and again it'll most likely hit an invalid code and it'll crash. For the same reason, you should not have int instructions or sysenter instructions in your patch area, because the program might be executing a kernel call and then you do the patch and then the kernel returns after the int instruction and lands into the middle of your jump instruction. In most cases, these things are not really a problem. Static analysis with IDA Pro is sufficient to find if a patch point is suitable. And I actually have a small IDA plugin that looks at a patch point and just tells me whether it's good or bad. Microsoft also has a hot patching implementation. It is used only in Windows 2003 Service Pack 1, but we'll probably see more of it in Vista and Longhorn. Because they have control of their toolchain, including the compiler, they took a slightly different approach than the third-party hot patching systems that we talked about earlier. In Visual Studio 2005, there is a new compiler option called /hotpatch, which adds the move EDI instruction in the beginning of every function. This is a 2-byte instruction that basically acts as a no-op. Also, if you use that compiler option, every instruction will have 5 bytes of padding before it, padding that is not used. When the Microsoft hot patch is applied, it replaces the first 2 bytes of the function, which are the move EDI instruction, with a short jump back to the padding. Then it puts a 5-byte jump in the padding area that goes to the hot patch DLL. This allows Microsoft to replace one function with its patched copy. While most of the other third-party patches limit themselves to just modifying a few instructions or maybe modifying a little bit of data and then returning back to the original function, the Microsoft hot patching implementation actually completely replaces the function. And what's most interesting is that they appear to have an automated tool that generates the hot patch by comparing the original and the patched binaries. And they can do this, they have the ability to do this because they have access to the private debugging symbols and the source code, which makes this kind of thing much easier. One limitation of the technique is that they have to replace the entire function. They cannot do something small. And they still have the same problems that everybody else has, which is if the problem requires an extensive redesign of the application or a change in major data structures, then their hot patching technique just can't deal with that. I think the biggest limitation of the technique is that it requires compiler support. If you have code that is not compiled with the /hotpatch option, then they cannot hot patch it unless they resort to other techniques, such as the ones we talked about earlier. And I think right now, Windows 2003, the latest versions of most of their operating systems are compiled with /hotpatch if you disassemble the files, but only Windows 2003 Service Pack 1 has patches that were released with hot patching support. And before we get to this, I have a short demo. I wasn't sure if I'll have time for it, but I think I do. Just in case anybody thinks that hot patching is like the brand new thing, here's a little thing. I think it's kind of cool. This is DOS 3.30 from 1987. And we're going to use the debug command to look at the interrupt handler for interrupt 21. This is the interrupt that DOS uses to execute it, to call it, that programs use to call the DOS system functions. And to look at the interrupt, we need to look at address 84, which is in the interrupt table. And the first 4 bytes that you see there, I hope you can see that. The first 4 bytes are the address of the handler that handles that interrupt. And this handler would be DOS code responsible for executing the system call. If we disassemble the code of the address, which is here, we see that basically it's a big switch statement on the AH register, which contains the number of the system function that we're calling. So this is what the code looks under normal circumstances. Now we're going to run the Frotto virus, which was, I believe, written in 1988. And it was a fairly advanced for its time virus. It had very good stealth capabilities. And it's also memory resident, which means that it stays in memory and it intercepts interrupt 21. And whenever you execute a program, it infects it. If we look at the interrupt handler again, we'll see that the address, the first 4 bytes, have not changed. And this is kind of unusual because usually in DOS, if you want to modify an interrupt handler, you would just replace the address in the interrupt table, and then your code will get executed. But this is not what the virus does, and that's part of a stealth technique to make it harder to detect. If we disassemble the DOS code, or the place where the DOS code used to be, we'll see that its first 5 bytes have been overwritten with a jump instruction going to the virus body. So the virus will execute its thing and then jump back to the original DOS handler, just like I showed in the slides earlier. So I just thought it was kind of cool. All right, so let's continue with the talk. In the third part, we'll go over some of the vulnerability analysis techniques that you need to use if you want to generate these hot patches. To some people, developing patches without having access to the source code seems like black magic, but it's actually not that hard. The process that you have to use is actually very similar to the exploit development process. Usually, to develop an exploit, you start with some kind of request or a file that is malformed and crashes the application. You would run it in a debugger, you would find where the application crashes, then you would use IDA Pro to reverse engineer the code around the application code around the location where the crash happens. You would try to find out what causes it, and finally you would write the exploit to take advantage of that crash and make it do something useful. The hot patch development process is very similar. Instead, in the last step, instead of writing an exploit, you end up writing a patch that fixes the vulnerability. So here's a collection of a few tricks. This is not organized in any particular way, but I just have a few tricks that I use to debug various kinds of vulnerabilities. If you have a Stack Overflow and you run it in the debugger, usually you're going to see a crash. If you have a full exploit that executes shellcode, then you're not going to see a crash. But in that case, you can replace the return address that's in the exploit code with an invalid address like 0, and then the program will crash. Or another alternative is to turn on DEP, which will cause the debugger to break in when you get to the first instruction of the shellcode, assuming that the shellcode is on the stack or on the heap. So once you find where the crash is, you want to look at the call stack and see how we got to that place. One problem is that Stack Overflows usually override a bunch of the stack, and you can't see the call stack anymore because it's overwritten. So to work around that, the solution is find the minimum amount, the minimum size of the request that causes the crash without overriding anything past it. So if you do this, you'll have a request that overrides just the return address, crashes the application, but the call stack that's above that will stay not corrupted, and you'll be able to look at it. The last return address on the stack will point you to the parent function of the function where the overflow happened. So once you have that, you can put a breakpoint there. You can trace through the execution, find the location where the vulnerability is. Heap overflows are a little bit harder to debug because there's usually a large gap between the time when the heap is corrupted and the time when the heap corruption actually overrides something useful. One solution is to use the debugging heap in WinDBG to spot heap corruption early on. I think this only works in XP Service Pack 2 and maybe 2003. If you know what location, if you have an exploit that overrides a specific location, like one of the pointers in the PEB, you can put a hardware breakpoint there and you can catch the write to that location. Once you have that, you can look at the call stack, and most likely the override happens in a free function, so you have to find out who calls the free function and on which memory block. Then, if you have a log of all memory allocations that happened before that in the program, you can match the block that is being freed against your log file and find out who allocated it. Once you know who allocated it, you can use reverse engineering techniques to figure out what this block is supposed to be, what it's used for, who frees it, who allocates it, and so on. There are a variety of methods for getting heap logs, but one that I use is these two conditional breakpoints in WinDBG that patch the free heap function and the allocate heap function, and basically they just print that there was a request for this many bytes and it resulted in this buffer, and they print the address of the buffer. And same with the free function. If you have an uninitialized variable problem, you have to find out what this uninitialized variable was supposed to be used for and who was supposed to initialize it. To find out who allocated it, you have to look at the address. If it's on the stack, then you can simply look at the stack frames of all the functions and find out which stack frame it's on. This will tell you which function this variable belongs to. Then you can disassemble the function and see what the variable is used for. If you want to find out who is supposed to initialize the variable, who writes to it, you could use a hardware breakpoint to catch writes to that location, but to do that, you need to send a non-exploit request, because if this is an uninitialized variable exploit, then nobody writes to the variable. So you have to modify your exploit to make it safe, to send a safe request that will trigger the initialization code, and then your write breakpoint will catch that initialization. If the variable is on the heap, then again it's a little bit more complicated. To find out who allocated this variable, you have to find out who allocated the heap block, and for that you can use the techniques from the previous slide. Finally, the most fun ones, if you have non-memory corruption vulnerabilities, such as directory traversals or a variety of other issues, you can't really debug them very well with a debugger, because you don't see any crashes, there's no memory corruption, you're not going to get any exceptions. So probably your best bet is to use runtime tracing. I think Process Stalker or a BinNavi might be useful for that. But it's still a hard problem. So if you can, I suggest that you wait for the official patch and then you just see what they fixed. So now we get to the most fun part of the presentation, and this is how to do vulnerability analysis and how to build a hot patch. And we're going to do this in about 15 minutes. Maybe more, if I have to explain more things. The vulnerability that we're going to analyze is the create text range vulnerability, which is cheating a little bit because I know what the answer is, and I've done this before, but I will still try to do every single step. So you can see how, even if the steps are easier because I know what they are, you should be able to see how if this were a new vulnerability, you can still follow the same process and get the same result, even if it takes you a little bit longer. So we're going to start with crash HTML, which is can you see that all right? Okay. We're going to start with crash HTML, which is a little HTML file that crashes Internet Explorer when you open it. And the important things in the file are this input element here, which is a checkbox. And then we have some JavaScript code which calls the create text range method on this element. According to the official documentation, create text range is only supposed to work for elements that contain text, such as text input boxes or buttons, but checkboxes and radio buttons don't have text. What happens when you open this HTML file is a crash in Internet Explorer, and here you get the window that we're all so familiar with. We're going to close it, and the first step of debugging this vulnerability is to open Internet Explorer and the debugger. So we're going to start Internet Explorer. We're going to pass the crash HTML file as an argument to get it loaded. And we'll let it run, and we see a crash. So take a look at so the crash is an access violation, it says here, and this is the address where the access violation happened. And it's an invalid address because there are no bytes there. This means that the program jumped to an invalid location, or probably called an invalid location. And to exploit this, you just have to fill the Internet Explorer heap memory with your shellcode. And if you allocate enough space and fill it with shellcode, chances are some of it will fall into that address. And for some reason, we always get that exact address when IE crashes. So if you have shellcode there and IE jumps to that location, it'll execute your shellcode, and we've exploited IE. But what we're interested in now is what causes the vulnerability. So let's look at the call stack. The call stack shows all the functions that were executed prior to the bad jump. And we're going to look at the last return address on the stack. And hopefully this will get us somewhere. I prefer IDA to WinDBG for looking at disassembly, so we're going to open MS-HTML in IDA. This will take only a few seconds. Bear with me. All right, so this is MS-HTML. Can you see this all right? I guess so. So we'll go to that address. This is the last return address on the stack, and we see a call instruction which dereferences ECX and jumps to it. So possibly this is the call instruction that jumped to the invalid memory location. To confirm this, we're going to look at the ECX register and the memory that it points to. And we see that it points to the first word in the memory is this 3C0474C2, which is the same place where we crashed. So this confirms that this call instruction jumped to the invalid memory. So what does this instruction do? If you've done any C++ reversing, you'll recognize this as a virtual call. ECX is supposed to point to a virtual table, and here we're calling the first function in that virtual table. So if ECX is the virtual table, then EDI must be the pointer to the object, because the first D word in the object structure is a pointer to the V table, and here we assign that into ECX before we do the call. So let's look at where EDI comes from, and we're going to switch to the IDA graph view because it makes things more clear. So we're interested in EDI. EDI comes from dereferencing EAX, but EAX comes from arg14, which is one of the function arguments. And from looking at it, we see that probably this function argument is a pointer to a structure, and the first field in the structure is the word 9, and then we add 8 to it. So the field at offset 8 in the structure must be our pointer to the C++ object. So the next step is to look at every place where arg14 is used in the function and make sure that it's not modified. And I'm going to skip that because it's tedious, but trust me, arg14 is never assigned to in this function, so it does come from the arguments that were passed to it. And here, if we look at arg14 in the arguments, it is the 1, 2, 3, 4, 5. It is the 6th argument of the function. So if we look at the function prototype, because it's a C++ function, the first argument it's an std call C++ function, the first argument on the stack will be this pointer. So arg14 would correspond to the 5th argument in the prototype, which is this thing. It's a pointer to a variant structure. And the variant structure is actually defined in one of the Windows header files. It is used for passing values around between JavaScript functions. It contains its first element, which we saw was 9 in this case, is a type identifier, which tells you what type of value is stored in the variant. And it can be a string, it can be an integer, a number of other things. 9 means VT dispatch, which indicates that the variant structure contains an object pointer. So it all seems to fit. And the object pointer, if we look at the definition of the structure, the object pointer would be at offset 8 in the structure. So now we have to find out where this variable comes from. And we know that EAX points to the object pointer. So EAX minus 8 will be our structure. So this is the variant structure. The first word here is 9, and then the D word is the object pointer. So if we look at the address of it, and we compare it to ESP, we'll see that they're very close. So this structure is located somewhere on the stack. Let's look at the call stack again. And the first column in the call stack shows us the frame pointer of each function. And if we look at where the address of the structure fits, we'll see that it belongs to the stack frame of this function, which is C script runtime run. So this means that the run function allocated this variable on its stack. So let's look at and it's located in JScript DLL. This is actually the location that EI patched. Let's look at the JScript file. So this is the C script runtime run function. And if we subtract this address from the address of the stack frame, we'll get the offset of that local variable, and it corresponds to var 70 because the difference between the stack frame and the variable is 70 bytes hex. And we see that var 70, we take the address of var 70, so we take the address of the structure, and then we pass it as the fourth argument of this function, which is invoke by disp ID. And looking at the call stack, we see that yes, invoke by disp ID is what the run function called to follow that path that led to the crash. So now that we know who allocated this variable, we need to find out whether the variable was left uninitialized, causing the crash, or if the variable was overwritten. So to do this, we're going to restart Internet Explorer. We're going to put a breakpoint at this place here, right where we take the address of the variable, and we're about to pass it. We let it run. And actually, this breakpoint will be hit twice, and the second time is the one that leads to the crash. Here we have the address of our structure. Here's the structure. We're going to put a hardware breakpoint that catches all writes to the third D word of the structure, which is the object pointer. So we want to find out if that object pointer ever gets overwritten. Put a breakpoint, run it, and the breakpoint doesn't hit. What does this mean? It means that the object pointer was never written to before the crash happened. So most likely, this is an uninitialized variable situation. The next step is to find out who is supposed to initialize this variable. And to do this, we're going to make a copy of crash HTML, or we'll call it safe HTML. We're going to edit it, and instead of a checkbox, we're going to use a text input field. Now, we know that the create text range function is supposed to be called on text fields, so this should work fine without causing any problems. We shouldn't see any crashes. Then we're going to restart Internet Explorer. Sorry, we're going to start Internet Explorer again, and this time we'll pass safe HTML to it. We still have our breakpoint in the run function, which allocates the variable. We run it, it hits twice. The second time is the one we want. Let's put a write breakpoint on it again and find out who writes to it. So here's our structure again. And you'll notice that the contents of that structure are actually the same every time. So apparently when we start Internet Explorer this way, it is deterministic. So we get the exact same behavior and the exact same memory layout every time. Let's put a write breakpoint there. Find out who writes to it. We'll let it run. And our breakpoint hits. And it hits in the cinput create text range function in MS-HTML. And in retrospect, it's kind of obvious that when you call the create text range function on an input element, then this would translate to a C++ call of create text range in the cinput class. But I didn't know that at the time. If we look at, we'll copy that address and then we'll look at it in IDA again. Okay, so here's the location where we initialize the variant structure. And if we take a look at the create text range function, we're somewhere inside it. And here's the beginning of the function. The easiest way to debug this is to put a breakpoint in the beginning of the function, then just see what happens. So we're going to restart IE again. and we're still running the safe HTML file. We don't need any of these breakpoints. We'll put a breakpoint in the beginning of create text range, let it run. So create text range executes. We're going to step through it, and we'll see how it establishes the stack frame. Then this is a check for one of its arguments being null. We pass that. Then there's another check for a bit field in the current object, and we check if bit 20 is set, and we also pass that, and then we continue, and then we call some functions, and then eventually we get to the initialization code. So now let's redo this again using the crash HTML file and see what the difference is. Okay. So this time we load crash HTML. We still have our breakpoint in create text range. Yes. We let it run. If we step through it, we want to find where the two paths diverge. We want to find what the difference is. And if we had something like bin naughty, this would be very simple, but we can do it in WinDBG2 manually. So first we go through the function prolog. Nothing interesting here. Then we do this check for the argument being null. We pass that again. Then we do the check for the bit field. We look at bit number 20. And now the branch is taken. So apparently this bit was set here, and it was not set when we opened the safe HTML file. And this leads us to a call to the setErrorInfo function. Let's take a look at the function in IDA. So here's the function prolog. Here's the check for arg4 being null. And if it is null, then we move this constant into EDI. And this constant is one of the standard Windows return codes. It's einvalidarg. And then we jump to this location here. And at this location, we call setErrorInfo, which sets the last error code, and then the function returns. So we're going to call this location setError and return. Okay. The argument to setErrorInfo, which is the error code, comes from the EDI register. The EDI register was just initialized, was just set to the einvalidarg return code. So apparently, if the argument is null, we return that error code because the argument is not supposed to be null. However, in both cases, safe HTML and crash HTML, we passed through this check, and we got to the second check here. That's a test for bit number 20 in this field in the object. And if that check fails, we jump directly to setError and return. And you can see the difference between these two cases. Here we initialize, on this path, we initialize the invalid arg. We initialize the return code and set it to einvalidarg. On this path, we don't. So when we call setErrorInfo, we're going to set the last error code to EDI, but EDI was set to 0, and we never changed it. So the vulnerability is a result of a missing assignment to EDI on this path. Because we don't set the error code, the program leaves it as 0. So the function aborts its execution, it exits, but the error code is still set to 0. What happens in the caller, and with a little bit more investigation we can confirm that, what happens in the caller is the caller looks at the error code to tell whether the function succeeded or failed, and since the error code is 0, it thinks that the create text range function succeeded. If it when it normally succeeds, it initializes that variant structure. In this case, the variant structure was left uninitialized because the function bailed out in the beginning. But the caller doesn't know that. So the caller will later try to use the variant structure that was supposed to be initialized here. So it's a miscommunication between the two functions. This function should return the proper error code. So now that we know what the problem is, we can try to fix it. And right now we're stopped right before the call to set error info. If we look at the ESP register, if we look at this is the stack, the last thing on the stack will be the argument to set error info, and it's 0. So we're going to replace it with 8070057, which is the invalid arg constant. And you can tell that I've done this before because I don't really remember Windows error constants off the top of my head. So now we have the error code on the stack as an argument. And if we let the program continue, we don't get a crash. Amazing. Instead, we get a little error message here. And let's open it. We get an invalid argument error on this line in the JavaScript code. So apparently the error code that we return gets propagated all the way up to the browser, and the browser displays it. And this seems like a pretty decent remediation because it is, in fact, an invalid call to execute this function on a checkbox. So this seems reasonable. So we know how to do it by modifying the stack, but now we want to do a real hot patch where we actually modify the code, so we don't have to intercept the execution every time. To do this, I'm going to open the opcode bytes here. I'm going to show. So these are the actual bytes of the program. So as I said earlier, the problem is that after this test instruction, we jump straight to the set error and return location instead of initializing EDI. It would be great if we could add a instruction here to set EDI, but unfortunately we cannot move the two instructions apart and insert stuff between them. So instead, we're going to change the target of this jump instruction, and we're going to make a jump back up here to the move EDI invalid arg instruction. So if we do that, after the test fails, we'll go back up here, we'll set the error code, and then we'll go back to set error and return. And it should work. If we look at the two opcodes of the function, 74 is the opcode, and 7F is the address that we want to jump to. This address is the difference between the target address. This offset is the difference between the target address and the current EIP. So if we want to calculate, the new offset, we should subtract. Or was it the other way? We will subtract the EIP. Okay, it was the other way. Subtract the other thing. So we subtract the current EIP from the target address, and we get ED. So if we replace the second byte with ED, our instruction should jump to the right place. So let's try it out. I'll remove all breakpoints. I will go to this memory location. Here we see the 747F bytes. I replace it with ED. And now to confirm that everything is fine, I will unassemble the code in memory, and we see that this jump now jumps to C277, which is up here, where we set EDI to, where we put the return code into EDI. So everything seems fine. I'll clear the breakpoints again, and I will run Internet Explorer. And now we can refresh this. I'm clicking the mouse, by the way. We can refresh this as many times as we want, and Internet Explorer does not crash. So if you actually want to turn this into a real hot patch, which can be deployed on a user system, it's just a simple exercise in C programming. You need to load your DLL, you need to find that location, change that byte, and you're done. What? Oh, because Internet Explorer has this thing where it only shows you the first error, and then it hides the second ones. It's an option you can set in the settings. It's to prevent scaring the users by showing them error messages. So that's the end of the demo. And now, before we finish, I want to say thanks to a few people. Rolf Rawls from Sabre Security for doing a great job on BinDev, which I use at my job every day. Ilfak and Derek for writing the patches that I talked about today. Good job. And of course, the Microsoft Security Response Center for giving us all the opportunity to actually do this and beat them to releasing the patch. So, thank you all. Any questions?